Okay, guys. Keep yourself muted,
Oh,
and if you have any questions,
okay.
just raise your hand,
Oh, sorry.
and we will just get started. So we don't lose any time. If you want to do a quick introduction, you can just type it in the chat, and everybody else can see that as well. Okay. Today's lecture is going to be about tracing, and as I mentioned previously, tracing is useful when you want to debug things that happen in order. And we can get a long way using traditional debugging by stepping the application, but traditional debugging is limiting in the sense that you can't always get an overview of the order of things, the order in which things happen. And an example of this is, for example, when we have threads switching between one thread to another, we can't easily see that in a traditional debugger. But with tracing, we can trace the changes in the switches between threads, and we can also trace things like mutex locks, and we can see when a mutex is being locked and when a mutex is being released, and we can add custom events as well. So tracing is a combination of debugging, using debugging tools, and using the software that actually runs on the microcontroller. So to make tracing possible, you usually add a little bit of code to the application that serializes the events that you add to your application, and then outputs those events in a suitable format that you can then load into an application that can display the trace from your application. So here on the image, you can see an example of what a trace looks like. And you can get a lot of very detailed information from the trace. So you can see how things relate in time and in the order in which they happen in the application, which can be extremely useful in specific cases where you need to debug timing of the application. So we have the most basic type of trace that everybody's familiar with is simply printing things out on the console. We're not going to talk today about that, but I just want to mention the different types of tracing that you can encounter in embedded systems. So print K, print F, that's the most common thing. You print out something on the console, you print out a variable, and you can see that variable in the console. The biggest drawback with that is that you can't easily process that data. You cannot display it in a tool that is designed for displaying traces, so it becomes a little bit limiting in that sense. The second common method is that you toggle a GPIO pin, and this is very useful because in some cases you don't actually have a timing budget to do tracing, as we're going to discuss today. So you're kind of forced to use those little bit simpler methods of tracing the application. And one such method is to simply toggle a GPIO pin or several pins and inspect the output signal with an oscilloscope. So you can connect different channels of the oscilloscope to the different pins, and then you can basically toggle those pins at certain points in the application. And by doing so, you can inspect the timing of the application and in what order things are happening. And that can be useful in very fast applications where you need to have where you have events arriving at a very, very high speed, like microseconds between events, in which case you simply can't afford to serialize those events and send them over to a debugging tool for inspection. So then you kind of forced to use GPIO pins. And but if you have the ability to have a little bit of timing budget that you can spare for instrumentation, then you can use the tracing methods that we're going to discuss today, and you can get much more detailed information about the execution of your code. So the way that the trace is happening is the tracing is happening on the chip, and we add extra code that serializes the event data basically that you want to send over to the trace. And we have a number of ways to get that data out of the chip. So one of the specialized ports on the chip on ARM microcontrollers, for example, is the SWO pin, which is a serial port, which is a transmit pin. It works like a UART, but it has extra hardware on the chip that allows you to push data into it. And it has an internal first in, first out queue, which caches the bytes that are going to be sent out to the debugger, and your code can continue executing whatever it is doing while the data is being transmitted. So that's very useful. You don't need to use a UART. You don't need to you don't need to worry about having to spend time in the UART interrupt. The SWO pin handles that for you, so it's very flexible in that sense. And this FIFO functionality is very useful when you have bursts of events. So, for example, if you need to send a number of events very quickly, and then there is a period of time where you're not sending any events, then the SWO pin can be filled up with data, and then it will start transmitting the data to the debugger, and your code can continue executing, and then you can send more events to this port. So that's one way. Another way is to just use a UART, which is available on all microcontrollers. But the biggest drawback with that is that it does take time to send data through the UART, and it can also, in certain cases, it can mess up your trace. For example, if you're tracing things like power consumption, or like you want to see, because if you fill out the UART, you have to then have code that actually runs and sends each byte. Or if you could use DMA, for example, and by doing that, you can put the chip to sleep, and the DMA will still continue running. But it's a little bit more involved to use the UART because it's a peripheral that you need to control, and you need to have a dedicated UART specifically for to be able to send data to the computer. You don't always have that. But one way that is always available is the JTAG port. So we can actually use the JTAG port, and we don't need anything else besides the JTAG port in order to be able to get the trace data out of the chip using GDB. And that's a very interesting way, and I'm going to show exactly how to do that. And not many people know how to actually just get a stream of data using GDB straight out of the application. And the tools that you need in order to display the data. So once you get the data out of the chip and you get it onto your computer, you can use a number of open source tools. And some System View is, for example, it's not open source, but it's free. And another pair of tools is the Trace Compass, which is a GUI tool, which is available as part of Eclipse. So if you install Eclipse and then you go to install plugins, and then you can install Trace Compass directly from Eclipse. And there is also a terminal application called Babel Trace, which reads CTF files. CTF format is a very simple format for serializing trace data. It's very lightweight, and it's very fast to serialize data in CTF format. And these tools, Eclipse, Trace Compass, and Babel Trace, they read CTF data. They can decode the CTF data and show it to you as a stream of events. And lastly, we have the Zephyr System View, which is a tool that is freely available, but it does require a special format that is used specifically by this tool. And there's libraries available for that. So for example, in Zephyr, you have System View support, which is an external library that is actually included that does the serialization of the events in the Zephyr System View format. So Patrick is asking, how can I raise my hand? There is actually a button by the. If you click on participants, Patrick, you can see a button there that you can use to raise your hand. There's actually a raise hand button. Another thing I'm gonna do is I'm actually gonna send everyone this document so you guys can access it in the chat. And you should be able to access the document. So here's a screenshot of the trace compass. This is what it looks like. We can trace things like interrupt enter, interrupt exit. And here is another view of the Babel trace, which shows the same events, but in the terminal. And this is the view of the system view tool. So it's a little bit more advanced. It has a much more graphical interface, and it shows a little bit more information included here. But one thing to note is that the types of events that you are tracing, that depends entirely of the code that you actually add to your application. So you actually add extra code to your application where you want to send data into the tracing buffer. And you do have to add the glue code so that you can serialize your application data and send it over, express it or serialize it in the tracing file format. So if you're using Zephyr as your RTOS and you're building an application on top of that, then you can enable tracing by enabling config tracing, setting that to yes. And if you want to use the CTF format, you then also enable the CTF format. The backend, there is a number of backends. So there is a system view backend, there is a UART backend, and there is also RAM backend. So RAM backend basically it writes all of the events into a buffer. And we can get the buffer out of the chip using GDB. So we can actually set a breakpoint using GDB, and we can retrieve the buffer. So I'm going to explain that a little bit farther down. But first of all, I want to talk a little bit about how the tracing is implemented. So this is what you need to do in your application in order to add tracing to your application. This is already implemented in Zephyr, but you still might want to add your own events. So it's good to understand exactly how it's implemented underneath. So there is a number of macros that compile either to simply no operation if you're not enabling tracing, or they compile to function names that correspond to a number of variables that you pass into the macro. So you get a number of functions that have a very particular format, and then you implement each one of these functions for each tracing backend that you want to use. So for example, for CTF, you're going to have a number of functions that start with sysport trace, and then for example, an object, basically functions that follow this template. This is this macro. These macros are basically defined in order to make sure that that all of the tracing functions follow the same template in each implementation. So it's just kind of like a helper. And then in code, whenever you want to send a tracing event, you call one of these macros, which translates to function call. And then this function call will in turn serialize the event, the tracing event, and then send it over either to the buffer if you use the buffer backend, or if you're using a UART backend, it's going to be serialized and sent over into the UART. So Pradney is asking if I can zoom in to the document. And guys, you can open the document yourselves. You should be able to open the document, and you should be able to zoom in for yourselves as well. And then you can see the text a lot better if you actually zoom in the document itself. So let me know if that works for you. But I think it should be fine. So for the CTF backend, for example, we have the implementation of these functions, and they basically resolve to C functions. And a C function like this that serializes the tracing events could look, for example, like this. So this is a tracing function for tracing threads switch in and switch out. So basically, whenever the scheduler is switching threads, it's going to call one of these functions, depending on whether you're switching in a thread or switching out of a thread. This basically queries the current thread, and then it sends the thread ID and the name of the thread to the specific function that serializes this event. And in this case, it's a CTF event. So it's an implementation of the CTF serializer that we're then calling here. And you can actually see what it looks like farther down. Let's see. Here we have an example of what it looks like. So one of these functions then, one of the CTF specific functions then calls CTF event. It's a macro, which basically sets up a static buffer inside that function and fills it with data. So there's a very smart way in which the CTF backend is implemented, which is completely static. So it actually allocates a static, like not a static variable, but it actually allocates a variable that is on the stack, but it's compiled. So it's defined during compile time using these macros. This macro accepts a variable number of parameters, and it's implemented for each up to 5 parameters. And so it translates basically into a small C buffer, which is filled with the data, and then it's serialized and sent into the backend. So in this case, if we're using the RAM backend, we're going to get data that looks like this. So this is a hex dump of the trace buffer. And at first, it's completely random data, but this data is actually very easy to understand. So we have our trace events. We have our trace events here. Let's see if I actually have a definition of the trace events. I actually have a small screenshot here of tracing CTF top. And this is a number, this is like a single byte that identifies the event. And if we look at this data, I can do a quick explanation of what this data represents. So the first 4 bytes of each event is a timestamp. Basically in ticks, in nanoseconds, in this case, a timestamp for when the event happened. And then there is a byte that identifies the event. So you can have 255 different events. And then there is a data field or event-specific data that comes after that. So in this case, it's number 19, which is in basically it's a hex number in this case. And that translates to the interrupt number. So 1C is actually an ID of an event that is interrupt exit, and the 19 is basically the data. So every time you are serializing events, they're going to end up in the buffer as a series of timestamp, event ID, and then event data. And you can define this data structure, this structure of this CTF stream. It is defined in metadata. So we're going to look at that as well, but I'm just going to explain first how we actually get the data out. So let's say we have added the instrumentation to the functions that we want to trace. Let's say we are tracing mutex lock and mutex unlock. So we have added sys trace mutex lock and unlock, and then those functions are going to be called whenever the program hits those points. And then the data is serialized and it's put inside a buffer. So we build our application, we program our application onto the chip, and then we need to, in order to get the data out, we are going to do that using GDB. So we start a GDB server, and one of the things, so you can use OpenOCD to start to connect to the JTAG adapter, and this will work on any architecture. So any architecture that is supported by OpenOCD, you can use this method on. So it doesn't depend on using Seger debugger, for example. It doesn't depend on using any specific hardware. It just requires that you can connect to the chip using OpenOCD. And basically, OpenOCD supports pretty much every architecture there is. So in this case, in this particular example, I'm using it with STM32. But any JTAG adapter that is supported by OpenOCD, you can basically use OpenOCD to start a GDB server. And in this case, you start a GDB server by simply supplying a command to OpenOCD. And the config here is going to be your board config. So basically, this is going to be the config that you use to flash firmware to your board. So it's going to in turn include like ST-Link and STM32L or F or whatever series you're using. So basically a standard config for OpenOCD that you normally use to flash the chip. But in this case, we're starting a GDB server, and we're then gonna connect to this GDB server using GDB. And the trace data, basically CTF trace data, is put into channels, which is every channel is basically a stream of CTF events, and we can put them into a separate directory, which in this case we call data. So we can delete those files first, and then we start basically GDB, and then we supply a GDB script for this session, which is actually going to append to this file. So it's going to recreate these files and append to them. So this is actually a separate command. We can just look at this as GDB, a separate GDB command. And we're gonna write the buffer that is being filled up with trace data. We're gonna write this buffer into these files, so we can then visualize those files using Babel trace, for example, or trace compass. And the reason I'm using a GDB script here is because I want to get the data automatically out of the application without having to type anything in GDB. So we can write a GDB script that looks like this, and this GDB script basically connects to the localhost port 333, which you can see here, which is the port that the GDB server has been started on. So OpenOCD is connected through the JTAG debugger to the chip, and we're connecting to the OpenOCD instance using GDB here. And then we want to set a breakpoint. So in this case, I set a breakpoint at a specific function where I actually clear the buffer. So the buffer is being filled up, and then when the buffer gets full, I basically clear the buffer and start from the beginning. And I can use this point in the application where I clear the buffer to basically set a breakpoint there, and then have GDB extract the buffer and put it into a file. And this is how you do it. So you set a breakpoint on the function, and then you can supply a number of commands. So basically break and then commands, and then until you get to end here. And what we do here is basically we append binary memory, and then we supply the file name where we want to dump the trace buffer. And then we specify the memory region that we want to dump into this file, which in this case is a variable inside the code that is called RAM tracing. And RAM tracing is basically a 4096 byte buffer that is being filled with trace data continuously. And the end position is basically the RAM tracing buffer plus the current position in the buffer. So it's not always going to be the last position, but it's going to be sort of one of the last positions, because the buffer is going to be first cleared, and then the next event is going to be written so that it can fit inside the buffer. So when we run this script, we basically end up with a stream of data that is coming out of GDB continuously, and it's being appended to the trace file, which we can then just open in Babel trace and extract and visualize the trace basically. So one of the things that is one of the drawbacks of using GDB in this way is that you're actually pausing the CPU. So in some cases, it will be better to trace using GPIO outputs when you can't afford any kind of interference with the application. So even if you use, for example, UART to push out the data, if you need to push a lot of events, you're going to have interference. So then in that case, it's better to use UART. But if you can afford a small pause where GDB can extract this buffer and then continue the CPU, then this works fine. And all the counters are going to be basically stopped, and the GDB will just extract the buffer, and then we have a continue instruction here, which will automatically continue. So this happens automatically, and as soon as the buffer is filled up, GDB takes it, and then the application just continues to run. And so you can then interact with your application, and as a result of this trace, you get basically a series of events that have been recorded inside this trace file. And the way that it's interpreted. So how does, for example, how does Babel trace know which data is contained in the events? So this is done using metadata, and there is a special metadata file which is located under tracing CTF TSDL metadata in Zephyr. So this metadata file contains, it's called actually a TSDL file, which is metadata for CTF format. And this is the description of the format that your particular application is using. So you can have custom events, you can have custom format for the events, you can send custom data, you can send, you can have integers, or 1 byte integer, 2 byte integer. You can basically have even enums, which, for example, here I define an enum for the current power state. So depending on which number I define here, I can then have in my visualization of this trace, I can see that the application has switched into runtime idle state, for example, instead of just number 1. So it's kind of easier to read. But you do have to define this metadata file in order to be able to decode the trace. And the trace itself is like, there is no way to resynchronize to the trace stream, because it's a very simple format, and it's designed to be very fast to serialize. So you do need to kind of get this trace from the beginning. So if you are, for example, if you're gonna trace a portion of your application, you should implement some kind of trigger that you can send to the chip to start tracing, and then you need to record the trace from the beginning, from the first event that has been generated, and then the tools, the Babel trace and the trace compass, will be able to decode the trace, but they will do so based on this metadata. So you do have to define the events here. Yeah, this is basically type aliases. So it's you define an alias here, and then it's called power state, and then you can use this power state as part of the struct definition for the event itself. So for example, here we have a power state exit event. We have the ID of the event, and we have 2 fields, the power state and the substate. So the event is going to have 2 variables, and then it's going to be decoded as 2 fields. It's kind of like type def, but this is a special script file. So this is not a C type definition. So this is a TSDL file. It's a special format used by CTF, the CTF file format for tracing, which in this case, this metadata describes the CTF file that you've been generating. So yes, Patrick, it's kind of like type def, yes. So what can we actually get out of this? So for example, if you have an application and you need to kind of see what is happening, we can look at this picture here. So in this case, we have a number of things happening. So there's interrupts being triggered in the beginning here. Then we can see from the trace, we can actually see that the application goes to idle mode here, which is correct. It's going to go into idle mode for 1.29 milliseconds. And then it's going to continue sending I2C data. So it's actually communicating over I2C here. And it's going to continue sending I2C commands, then sleeping for 1.2 milliseconds, and then sending a little bit more I2C data. And then it's going to have a long period here which we can actually see from the trace that this period is actually, the CPU is actually working. So it's not switched out. The main thread is switched in, and it's actually working. So when we see something like this, we can actually look into the code and try to understand like what is actually going on here. Why is the CPU working for this period of time here, and basically quite intensely, and then the CPU goes to sleep here. So we can start looking through the code, and we can discover interesting things in the code. For example, stuff like this. There's a while loop here that waits on the GPIO pin, and then basically the program sleeps for 1 millisecond, and then it's gonna go back to this loop, and then it's gonna sleep for 1 millisecond. And this is typical kind of crap that you find in code that comes from Arduino libraries, because this should have been implemented using a semaphore. So this should have been implemented using a semaphore that is given from an interrupt, and then this should basically sleep on a semaphore, not loop in a loop like this. But this is actually not the culprit. This is actually not what is generating this pause here. The pause is actually generated because during this time, the application is writing into the internal EEPROM of the chip. And this process takes a very long time. It actually takes a long time to write to the internal EEPROM. And this code actually ends up consuming a lot of CPU power here. So we can discover things like this, and we can kind of see how can we optimize the application. So for example, if in this case we wanted to optimize for power use, for how much power the application is using, we can optimize things like this. So we can look at, maybe we can put this this call to save things in the internal EEPROM. Maybe we can put it somewhere else, or maybe we can do it less frequently, so that we can sort of put the chip to sleep and not have to consume power during this time here. But it kind of depends on what the application is designed for. And in some cases, it's very important to conserve power. In other cases, you might just want to inspect things like, for example, are you utilizing the CPU properly? Like what kind of thread switching is taking place? So you can trace each thread switch event, and you can see sort of how the application is switching between threads, and if there is anything that can be optimized there. So tracing can reveal a lot of information that is time dependent. So the time and order dependent information. So in that sense, it can be extremely useful. And here's another trace. Here I have actually switched this application to use SPI interrupt driven mode. So in this case, we are actually seeing SPI interrupts here happening. So because we are tracing ISR enter and ISR exit, we can actually see every single SPI interrupt. And one of the interesting things that you can see if you look at this trace is that the application never actually enters into any kind of idle state. It's actually it runs an interrupt, and then the interrupt exits, and then the interrupt is called again. So it basically goes round and round. So using interrupt-driven mode doesn't actually improve the performance of the application. One of the other things, so here's, for example, a definition of power states, which I've discussed in the previous lecture, where we looked at how to define the power saving modes for STM32L0 chip. But using tracing, we can actually see how the CPU is utilizing those power modes, and when it actually enters into idle state or deep sleep state. And this is really, really useful for debugging. Debugging things like when does the CPU actually, when does the power system actually set the CPU into a particular state? And we can see that because we've added the power state switching events here. Let's see. Here, and we can actually see that the CPU is entering into idle state here, and then it comes out of idle state, and then it's basically receives a few interrupts, and then it switches to main thread, or switches out the main thread, then switches in the main thread again. And then eventually it will go into suspend to RAM state, which is exactly what we want, because we have defined it here in this device to configuration. We have defined the different power states. So if we have a long sleep period, then we switch to the suspend to RAM state. If we have a very short period, then we just switch into suspend to idle state. In which case the CPU is just it's just idle. It's kind of sleeping, but everything is running. Like all the peripherals are running, so it's not in deep sleep, as it's called. And yeah, and this is this gives a very detailed overview of when things are actually happening. So here is a short description of, just in case you're curious, of how this is actually serialized. So here is the serialization code, and it's written in a number of macros. And I think this is beautiful. I think this is a beautiful way to code for the C preprocessor, because it's kind of like it's almost like magic, because you end up with a very simple macro that serializes all the event data. And this is how this macro is implemented. So it's basically copy pasting parts of the code, and eventually you end up with a serialization code that compiles into an array here that we actually dynamically size. So we use the map macro here, which is defined here. And this map actually adds size off every single, so it calls size off on every single parameter that is passed to this macro. So the end result is that the packet is going to be the total size of the event. And then we can write these parameters into this buffer, the packet buffer, using the same map macro, which calls another macro for every element that you pass into the map macro. And so basically we pass the variable arguments here. And then you call the tracing format raw data with the packet, which writes it into the tracing buffer. So this is a very neat implementation of tracing, which you can also find in the Zephyr code repository under subsystem tracing. Yes. So Sebastian is asking, is there a chance to use this type of tracing with Bluetooth stack due to pauses you mentioned? Well, you should be definitely able. I don't see why you wouldn't be able to use it with a Bluetooth stack, but because you can actually determine yourself. You have full control of when you pause. So you can write your code, like you can add a certain function to your code where you will then place a breakpoint on which GDB will break, and then you can dump the buffer at that particular point. So it doesn't have to be, for example, like I'm using, let's see here, if I go back to my GDB script here. So I'm using a function which I've added myself actually, which I call tracing clear RAM, which is a function that just moves the pointer of the tracing buffer to the beginning of the buffer. And I break there, but you don't have to break. Like you can literally write your own function where you put the breakpoint, and then you can extract the buffer, and then you can continue the application. So you can determine exactly at what point you are extracting the tracing data. So you can have your application run without any interference and record everything that happens. And then at a certain point, you just break the application, you pause it for a short while, you grab the data out, and then you continue the application. And this happens basically automatically in sequence, because I'm using append binary memory here, which means basically append the contents of this buffer into the file. In this case, data/channel00. So you have full control of when you're going to be pausing, and hopefully, if you like, depending on how you're using the stack, you can place the breakpoint at a suitable point where it doesn't interfere with your application. So that's one of the things that is good about using like GDB directly, because you have a lot of control of when you extract the data. So you can literally have a very lightweight tracing in place that just writes to memory, and then you extract the data in one go when it's the most suitable to extract it. So yeah, and here's the implementation of the actual backend that writes into a RAM buffer. So this is the RAM tracing variable that we are dumping into the binary file, and here's a function. And the only reason I have this function is because I want to set breakpoint on it very easily. So I want to be able to just set a breakpoint on this function. So that's why I put this pause equals 0 into a separate function, which allows me to set a breakpoint there. And so when the buffer is full, this function is going to be called, and GDB will break, and then the data will be appended to the file on the computer. And that's how we can get the tracing data out. So we're going to transition into a short questioning stage here. But first, I want to mention some resources. So you have the CTF file format here, common trace format. And you have the Zephyr tracing documentation here, which is the docs for the tracing subsystem. And we also have this resource, which I found interesting. So this is a tech talk about advanced troubleshooting of real-time systems. So hopefully you can learn something from there as well. So that's it for this lecture, and I hope this was useful. Ibrahim has a question, so I'm going to unmute you. So Ibrahim, you can unmute yourself.
Hello, can you hear me?
Hello, welcome.
Yeah, thank you. So basically, it was like during, it wasn't a question, but just an appreciation that it was like a very good to know the tracing thing, because I'm from Pakistan, working as an embedded engineer, and this tracing thing is very useful while we are like troubleshooting the embedded system, because we don't know, sometimes it's very difficult to troubleshoot things. So it was a very good lecture, and hope it might help us all.
Awesome. Thanks. Yes, this is very useful, and it also provides you with a much richer set of data. Like you can output a lot of data, and have a very structured way of viewing that data. So it's very useful in that sense, compared to, for example, using printf, for example, to print variables onto the console.
Yeah.
How about everybody else? Does anybody else have a question? Okay, if we don't have any more questions, then thanks for being here, and I'll see you next week.
Yeah, thank you so much once again. Take care.
Bye-bye, everyone.
Bye-bye.
Bye.